So Mrs. Gallus and her students decided to perform the caffeine experiment. In their experiment, 10 students were randomly assigned to drink Coca-Cola. Nobody calls it cola. Coke. With caffeine, and remaining 10 students were assigned to drink caffeine-free Coke. Were their findings statistically significant? So today we're going to talk about statistically significant. So the table shows the change in the pulse rate for each student, final pulse rate minus initial pulse rate, along with the mean change for each group. Okay, so there's the data right there. So we're going to find the difference in mean pulse rates for the group. Does your initial reaction lead you to believe that they found evidence that caffeine does or does not increase heart rate? Explain. Okay, so I'm a caffeine fiend. I don't know if y'all noticed, but I have normally coffee and like 3 energy drinks, and like it's a problem, it's fine. But that being said, does it increase your heart rate? Most of us think yes, but how many of y'all can drink like a Mountain Dew or a Coke right before you go to sleep and like not even think twice about it? Most of Americans, right? So the mean difference is you're going to take the mean for caffeine and then the mean for no caffeine and subtract them. Okay, so 3.2 minus 2 is 1.2. Now let me ask you this. Do you think that they found evidence that caffeine does or does not increase heart rate based off of that? No, why not? Okay. 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 All right. So, but it could, but it's not necessarily like solid information, right? Like 1.2 difference really isn't that much. Like maybe they did a couple jumping jacks after they drank the Coke, or they did it. You know what I mean? So we're going to say possibly, but a difference of 1.2 isn't that big. Okay? So what are 2 possible explanations for the difference in mean pulse rate? What are 2 possible explanations for the mean pulse rate? Well, one, that caffeine caused the change to happen, right? And 2, that it was just a coincidence that caffeine group, I'm going to call them CAF group, had a larger change. Okay, so again, could be coincidence, and kind of depending on like the type of person, like females are going to have more of a reaction to caffeine than males are. Okay, depending on if you're taking medication, could impact your caffeine intake and how it affects your pulse rate. Okay, so we're going to assume though number 2. Okay, just like what we said, there's a 1.2 difference, not really that big. So it's just a coincidence that the caffeine group had a larger change. Okay. So to try to decide if the difference in pulse rate is big enough to be convincing, we're going to do a simulation with the data. So a simulation. Step 1, gather 20 index cards to represent the 20 students in the experiment. On each card, write one of the 20 outcomes listed in the table. Okay. For example, write 8 on the first card, 3 on the second, and so on. Step 2, shuffle the cards and deal into 2 piles of 10 cards each. This represents randomly assigning the 20 students to the 2 treatments, assuming that the treatment received doesn't affect the change in pulse rate. The first pile of 10 cards represents caffeine group, the second pile of 10 cards represents no caffeine group. These are my results when I did that. Okay, so I did 20 cards. Normally we would do it, but COVID. Okay, so go ahead and write these in your table. And for right now, we're all going to have the same data because COVID. It sucks. I'm sorry. The mean. So we're going to find the mean change for each group. So what we're going to do is we're going to take all of this mess, add them up, and then divide by 10. So we're going to say 3 plus 5 plus 1 plus 4 plus 5 plus 0 plus 6 plus 1 plus 4 plus 0. And then divide by 10. So that's going to give me a mean for the caffeine group of 2.9. It's going to give me a mean for the caffeine group of 2.9. And then we're going to repeat that process for the other one. Yes, include those negative numbers. So 8 minus 2 plus 4 minus 1 plus 5 plus 4 plus 3 plus 1 plus 2 plus minus 1. And then divide by 10. So that's going to give me a mean of 2.3. So now it says for me to subtract the means. Okay, so I'm going to take 2.9 minus 2.3. What am I going to get? 0.6. Is 0.6 that big of a difference? Not really. That's like not even that important to mention, right? Okay, so add your difference in the means to the dot plot on the board. Normally we would do this as a group. Again, COVID. This is a rough sketch of what the dot plot looked like for one of my classes. Okay, so we've only got 4 that are above that 1.2 area, and then we got a bunch down here. It doesn't matter right now about the numbers particularly. So if you want to just do a rough sketch of that dot plot, that's okay. But what does each dot represent? What does each dot represent? So I would put a dot at 0.6, right? What did that dot represent? Say it again. There you go. So the difference in means from one trial, right? And we're trying to figure out if caffeine has no effect. So we're trying to figure out if caffeine has no effect. Okay. It says what percentage of the dots are greater than or equal to the difference in means of 1.2 found in Miss Gallus's experiment. So what we're going to do is we're going to total up however many dots we have and then look at the ones that are greater than or equal to 1.2. So if I go back to my sketchy dot plot, okay, I'm going to count. I got 1, 2, 3, 4 dots. Sorry, my board is like freaking out. Okay, I got 4 dots over here out of 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 4 out of 18. Go into my calculator, 4 divided by 18. That's not 18. It's 22%, right? So 22% are bigger than that 1.2. So it says interpret this percentage. So what we're saying is assuming caffeine has no effect on heart rate. Oops, yep. There is a 22% probability of getting a difference of 1.2 or more purely by chance. So do you think that the difference in means we found from our experiment is due to the caffeine, or has it occurred purely by chance? Okay, So here's your takeaway for this. If your percent is less than or equal to 5%, then yes, it is pretty unlikely to happen on its own. So it is probably due to caffeine. Okay. Ooh, that's spelling though. If the percent is bigger than 5%, then no, it's not that unlikely. It could be a coincidence. Okay? Another fancy way to say this is that it's statistically significant or not statistically significant. Okay? So in our case, we had 22%, right? So no, it's going to probably be a coincidence, right? So the big ideas from this, so this is on that last page, okay, or the third page, second page, whatever you want to call it. So the big ideas are sampling variability. So different samples yield different estimates. Okay, so just like we were saying, if we would have ran that simulation again, we probably would have gotten a different percentage. Okay, larger samples produce more accurate estimates. If I have 50 people out of the population versus 100 people out of the population, that 100 people is going to give me a more accurate estimate, right? Okay. Margin of error, which creates an interval of plausible values. So you're going to take your sample estimate and either add or subtract that margin of error to see how far outside of it would be. Statistically significant, when results from a study are too unusual to have occurred, I can't say it again, occurred purely by chance. And again, that whole, if it's less than or equal to 5%, it's statistically significant. If it's greater than 5%, it's not statistically significant. Okay. Dealt with this a lot with psychology. You're going to see that a lot in those kind of experiments. Okay. All right, so it says, how much do National Football League players weigh on average? In a random sample of 50 NFL players, the average weight was 244.4 pounds. Pretty big dude, right? So do you think that 244.4 pounds is the true average weight of NFL players? Explain your answer. Do you think all dudes who play NFL are actually 244 pounds? No, okay? And why is that? Well, just like what we were talking about earlier, all samples are different, okay? If I just pull random players, some of them could be wide receivers. Normally those are like your kind of smaller guys. You know, some of them can be, you know, the offensive line. That's going to be a little different, okay? So if you pull different samples, probably going to get different results, right? So since we don't have the whole population, we don't expect sample mean to be the same. All right. If another random sample of 50 NFL players was taken, would you expect the same average weight of exactly 244 pounds? Just like we said in the last one, no. Okay, because every sample has a different group. So we're not going to have the same exact mean. Okay? Estimates are usually within a margin of error. The margin of error for the estimate of 244.4 pounds